All right, guys, good morning. In this tutorial number 8, we will be discussing about how we can design filters, and we will be understanding different types of filters, right? So over here, there are several different types of filters. The first one is we call as low pass filter. So for low pass filter, you have a response to somewhat. We have frequency over here, we have amplitude, right? And it will allow some of the low frequencies till the cutoff frequency. The next type of filter that we have is called high pass filter. And the difference is that for a high pass filter, for the x-axis of frequency and on the y-axis of amplitude, it will only allow the high frequencies after the cutoff. So that's the region that will allow, and that is the region that it will allow, right? The third type of filter that we have is called a band pass filter, in which you have the liberty to allow frequencies with certain range, FC1, FC2. So there will be two cutoff frequencies, and you can have the maximum amplitude in between the two cutoff frequencies, right? So that is the third type of filter, which is called band pass filter. And last but not the least, the fourth type of filter is band stop filter, which will allow all the frequencies below FC1 and above FC2. Here we have the amplitude, right? So this is the region that is like allowing the frequencies, and it will stop the frequencies only at certain region. All right, so with that being said, there are like four types of filters that we normally have uh, to work with. Uh, Now we need to understand how do we like specify or divide the type of filters. For example, if I say that I have to design a filter, then I have two options here. I can design filter using active components, right? Or I have the liberty to design a filter using the passive components. What we mean by passive components is that we can design a filter using resistor, capacitors, and inductors, right? Which are the passive components. And if we design a filter using active components, which are operational amplifiers or even transistors. All right, so a quick discussion on these different two types of filters. So for passive filters, we know that it's because it's RLC circuit, right? So the output is always going to be less than your input, right? So the disadvantage, I would say, or the biggest difference between these two type over here is that the output for a passive filter is always less than input, because of R and C and L combinations, you will probably have lost the voltage, or the voltage would have been reduced, right? Whereas on the other hand, if we talk about the active components, as you know, the transistors or the op amps will provide eventually a gain, right? So you would have a gain from here, which will eventually be, right, you can have more output. So that's the biggest advantage over there. One of the another important difference between passive and active components is that for passive components, you cannot control the loading on the circuit. What we will later on see that like one of the RC filter would be like R and C, and that is your V in and that is your V out, right? It is a low pass filter, but as you can see, as I connect the load over here, then the loading effect will be on this whole circuit, right? Whereas for an operational amplifier, we have no connection between input side and output side, right? They are like isolated from each other, the both of the circuits. So it doesn't affect the loading on the circuit. So that's a big advantage of using active components, as that there is no loading effect. Whereas for passive components, circuit can get loaded and its values disturbed depending on the output resistance, right? Over here, it's totally isolated, so it doesn't really matter whatever output you are going to connect on that side or whatever load you are going to connect on that side, right? So basically, active components are good, and active using the active components, if you design filters, that will be more useful. Now today we are going to start our first thing, which is using a low pass filter using passive components, which is R and C, right? So the basic form that you would have for a filter is like you have a resistor over here and it has a capacitor over here and it is giving some output over here. So that is your Vin, that is resistor, that is capacitor, and that is your V out, right? The formula for the gain or the formula for output can be written as, it's just a voltage divider, which is V out is equals to XC over XC plus R times V in, right? As you know, XC is what? XC is the um it is the impedance for the capacitor, right? So XC can be written as 1 over omega C, or it can be written as 1 over 2 pi F, which is omega times the capacitance. Now let's try to analyze this circuit. For example, if we have a very small value of frequency, which means, let's say frequency approaches to 0, right? Then this whole value would be very large. For example, 1 divided by very small value would give me a very large answer of XC, which in turn, when I substitute it over here, would give me the maximum output, which is, for example, 100 over 100, right? R would be like very negligible, which means that if I have smaller frequencies, I would probably have the output over here, which makes sense because for a low pass filter, you have output on lower frequencies before FC. Let's try that again with, let's say if I take that F approaches to infinity, right? So when it's like a very big value in the denominator, this whole value would turn out to be approximately 0. And when this value turns out to be 0, then this 0 multiplied by whatever Vn is, the output would be 0, which means that for on higher frequencies, you will not have output. So that is just the relationship discussion or conceptual discussion of why we are not getting an output uh, using the higher frequencies, right? So the circuit is designed in such a way that the output frequencies are stopped and only the lower frequencies are passed. A quick question on what we discussed so far. So let's say if I have a source of 10 volts at 2 kilohertz frequency, and I have a resistor value of 1 kilo ohms, and I have a capacitor value of 0.1 microfarads, right? And that is my output point over here. So the question says find cutoff frequency, and it says find, that's your part A, that's your part B, says find output voltage at 2 kilohertz, right? And part C says sketch sketch the plot, right? So the first part is about finding the cutoff frequency. The formula for cutoff frequency is Fc is equals, for an RC circuit, is 1 over 2 pi RC. So I plug in the value of 1 kilo ohms over there and 0.1 microfarads over there. My frequency of cutoff turns out to be 1.59 kilohertz, right? So that is the part A answer over there. All right. After part A, I know my FC turns out to be 1.59 kilohertz, right? Let's try to solve for part B. For part B, it says find the output voltage as 2 kilohertz, right? So for part B, I would first need to figure out what is my XC. So my XC is 1 over 2 pi FC, which is when I put in the value of frequency of 2000 or 2 kilohertz and multiply that with the capacitance of 0.1 microfarads, I'm getting an answer of 796 ohms, right? So as you know, these are like XC and R are like vector quantities, right? So your V out equation would be the magnitude of XC divided by the root RC or R resistance over there square plus XC square, right? So that would be times the Vn. So if I plug in the value of 796 on top and 796 square plus a 1 kilo ohm, which is 1000 squared times 10 volts, which is the input signal over here, I will get the output of V out is equals to 6.22 volts. So that is the answer for my part B over there. Right, so that is the answer for my part B over there. Now let's try to sketch this or plot this. I'm going to write that as 2 kilohertz. I'm getting a voltage of 6.22 volts, right? All right, so if I try to plot for the part C over there, I'll probably say that I have something like this as a plot, frequency over here, and let's say it's just an amplitude in volts because I'm plotting it over there, right? So my cutoff frequency is somewhere, the graph would be somewhere like this, and then it decreases for a low pass filter, right? Add an attenuation of 3 dB because we know that the cutoff frequency lies after an attenuation of 3 decibels minus 3 decibels. It would be over here, which is 1.59 kilohertz. And I can mention one more thing. At 2 kilohertz, I'm getting 6.22, right? I can say that at 2 kilohertz, I will get a value of 6.22 volts. So this is my sketch for all three parts, A, part B, part C. All right. So this circuit over here is a passive RC low pass filter, right? I'm going to touch upon one of a very quick concept over there. This gradient of this slope would be minus 20 dB per decade, right? If I want to make and design a filter in such a way that the slope is like very steep over there. For example, if I wanted to do something like that, if I have a red marker over there, or maybe I should zoom out first. Right, so if I go and if I wanted to have somewhat uh, gain to this, or even I would say more reduced, more reduced decade gain, more reduced uh, slope, or even steeper slope, I would say, then this red line over here is my design requirement. So it can be a minus 40 dB per decade. And this blue line over here is can be minus 60 dB per decade. So you need to know how you can make that, right? So this circuit over here is just a 1 RC circuit with a 1 resistor and a capacitor, which is a first order circuit. If I add the order to the order 2, right? If I had the second order and then I take the output, then I can actually reduce my decrease of this, like my slope, and I can make this as a sharp filter. So this will be now my second order circuit, which has a slope over there of minus 40 dB per decade. So as soon as we increase the order of the circuits, the slope would start to decrease, and you can actually design such filter which is like very steep in nature so that your design requirements are fulfilled. All right, so that is all about the passive RC low pass filters and what would happen if we cascade the circuit to a higher orders. Thank you so much.